Welcome to the session number 12 from the playlist of electromagnetic induction. The topic is the mutual inductance, and based on this topic I have written here 4 important points which will help us to understand this topic in brief. So the first point is the definition of mutual inductance, and the definition of the mutual inductance is that it is the magnetic flux linked with one coil when the current flows through a nearby coil. So in order to understand this definition, I have made one diagram here in which there are two coils which are placed near to each other. So this is the coil number 1, this is the coil number 2. In the coil number 1, a current I is flowing through it as indicated by these arrows, and this is the primary coil. And there is another coil number 2 which is situated near to this coil number 1, and this is the secondary coil. So mathematically, the magnetic flux which is linked with the coil number 2 due to the flow of the current in the coil number 1 is equal to N phi B2, which is equal to M into I, where M is the mutual inductance for this pair of coil, I is the current which is flowing in the coil number 1, and phi B2 is the magnetic flux which is linked with the coil number 2 due to the flow of the current I in the coil number 1. And here N is the number of turns in the coil. So the induced EMF in the coil number 2, that is E2, this is equal to minus N d phi B2 upon dt. Now here the value of N will be equal to 1 because the coil has got only one turn. So induced EMF will be equal to minus d phi B2 upon dt. Now phi B2 will be equal to M into I. Now if I put this value M into I in phi B2, then I will be getting this equation, that is minus M di upon dt, because the mutual inductance for this pair of coil M is a constant value. So minus M will be taken out. Sorry, this M will be taken out. So finally I will be getting the value of the induced EMF in the coil number 2 as minus M di upon dt. So we can also say that this N d phi B2 upon dt is equal to M di upon dt. And from this equation, that is N phi B2 is equal to M I am also getting the value of the mutual inductance as N phi B2 divided by I, where I is the current which is flowing in the coil number 1 in this case. Phi B2 is the magnetic flux which is linked with the coil number 2 in this case, and N is the number of turns in the coil. Now from this equation we can see here that the induced EMF is equal to minus M di upon dt, that is EMF will be induced in the coil number 2 only when the current is changing with time in the coil number 1. di upon dt is the rate of change of current with time. Second important point is that the coupling coefficient K is equal to the magnetic flux which is linked with the secondary coil. Here the primary coil is the coil in which the current is flowing, and the secondary coil is the coil in which the induced EMF is generated. So the coupling coefficient K is equal to magnetic flux linked with the secondary coil, that is the magnetic flux linked with this coil number 2, divided by the magnetic flux developed in the primary coil, that is the magnetic flux developed in the coil number 1. Now the value of the coupling coefficient, it ranges from 0 to 1, and its value is generally less than 1 because of the flux leakage. And the value of K depends on many factors like the distance between the two coils, their relative position, the material which is surrounding these two coils, and the magnetic properties of the core on which these coils are wound. Now the third important point is that for a pair of magnetically coupled coils, the mutual inductance is also given by K multiplied by under root of L1 into L2, where L1 and L2 are the self-inductance of the two coils. And the last important point is that for a pair of concentric circular coils, M, that is mutual inductance, will be given by mu naught into mu r into N1 into N2 into pi small r whole square divided by 2 capital R. Here small r is the smaller radius, capital R is the bigger radius, N1 and N2 are the number of turns in the two coils, mu r is the relative permeability of the core, and mu naught is the permeability of the free space. Similarly, for the pair of solenoid coils, for the pair of solenoid, the mutual inductance, or you can say for a pair of solenoid coils, the mutual inductance is equal to mu r into mu naught into N1 into N2 into A divided by L, where mu naught is the permeability of the free space, mu r is the relative permittivity of the core, N1 and N2 are the number of turns in the two coils, A is the area of cross section, and L is the length of the coil. So thank you very much for joining this session. In the next session, I will be coming up with one question pertaining to this topic of mutual inductance. So till then, have a nice day. Bye.